Hello, viewers. Hello. 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 Hello, everyone. We'll get started in just a moment here. I'm waiting for the number of viewers to increase. Hope everyone had a nice weekend. I'm all right after this. I'm going to hop on the stationary bike for an hour, and I only have like an hour and 10 minutes before I have to be back for office hours. So I'm just being efficient here. I'm literally, after this class is over, I'm going to run to the stationary bike and start exercising. Haven't been exercising outside because of the bad air quality for the past few days.
Hello, Hazel. Hello, Hazel. What you do?
I'm going to wait about one more minute and then get started. Hello, Geography Genius. Oh, Hazel. Oh, Hazel. Oh, come here. Come here. Oh. Oh, yeah, we do match. What you do? What you do? What you do? Okay, you go bye-bye. All right, I think we have enough to get started. Yep, we do. All right, so hello, welcome. Today we are going to be learning about some more difficult kinematics equations problems. So let me switch to my document camera. So at the end of the last lesson, I used calculus to derive three equations, okay? The first equation was x of t equals x initial plus v initial times time plus 1/2 at squared. Okay? So this is the same kinematics equation that we used last year. Last year I wrote it as delta x equals v initial times time plus 1/2 at squared. But this is a little more mature way of writing the equation. So you might recall that delta x is x final minus x initial. So we've added the x initial term to the other side, and we're writing x final as position at time t, okay? So this is kind of like f of x, right? Position at time t, function at value x. So it's a more mature way of writing it. We can also write v of t, the velocity as a function of time, is v initial plus at. And then we also learned the equation that v squared equals v initial squared plus 2a delta x. So you do not need to know how to derive these equations, but you do need to know how to use these equations. Okay? Now, the key caveat for this is that if you are going to use any of these three equations, the acceleration has to equal a constant. Okay? All right? The acceleration has to equal a constant. So, what we're going to focus on today is advanced problems using these equations. So last year I kind of gave you some softball questions regarding this. Hang on a second. Hazel's getting into something. Hazel? What are you doing? Come on. I'm trying to feed Hazel a diet because she's getting a little bit overweight and she's just so hungry all the time. She's just constantly on the searching for food. Okay, so back to our question. So the first type of question that we're going to talk about is collision problems. So let me go ahead and write a collision problem as an example, okay? So let's suppose two cars are separated by 1,000 meters, okay? Both cars start at rest. All right. At time 0, the left car accelerates right at 14 meters per second squared. The right car accelerates left at 22 meters per second squared. Okay? So let's understand this scenario. We've got two cars. One of the cars is at x equals 0. The other car is at x equals 1,000 meters. Okay? And at time 0, they both start accelerating towards each other. Okay? So they're going to have a collision. Now, where is that collision going to occur? That's what we're trying to figure out. Okay? The halfway point, if they both have the same acceleration, then they would meet exactly in the middle. But we can see that the right car has a greater acceleration than the left car. Okay? So that means that they're going to accelerate, but this one's going to travel further. And so the collision is going to be somewhere to the left of the center. Okay? So we're going to figure out where is the collision. And the strategy for collision problems is we want to figure out what is the position of the first thing as a function of time, and what is the position of the second thing as a function of time. And then if they've had a collision, we have x1 equals x2. So that is how we are going to solve a collision problem, okay? Now, to find the positions as a function of time, I'm going to use this first kinematics equation. So, for the car on the left starts out at position 0, so x naught is 0. It starts out at rest, so v naught is 0. And then we have plus 1/2 at squared, so 1/2 a would be 1/2 of 14, which is 7. So x1 of t is simply 7t squared, okay? Now let's figure out x2 of t. Now x2 does not start at the origin because the second car starts at position 1,000 meters. So my x naught is 1,000. It also has no initial velocity, so that initial velocity term is going to be 0. All right. There's a question, wouldn't the t term be 0? Well, t equals 0 is where the clock starts, okay? So t is not going to be equal to 0 in this problem, okay? Because we're letting time advance beyond time 0, okay? And then the initial velocity term is 0 because the second car also starts at rest. And then we have an acceleration of 22 meters per second squared left. So that's going to be negative 22 meters per second squared. And we divide that by 2 to get negative 11 t squared. So the second car's position as a function of time is 1,000 minus 11 t squared. Okay. So to figure out where they collide, we first would figure out when they collide. So we'll set x1 equal to x2. So we have 7 t squared equals 1,000 minus 11 t squared. So this equation expresses the collision, okay? And so I'll add the 11t squared over. I get 18t squared equals 1,000. I can solve for the time at which the collision occurs. Um, 7.5 seconds. So the collision happens 7.5 seconds after time 0. Okay? Now, if we want to figure out where the collision occurred, we can plug this time into either of these two equations. Okay? In fact, a great way to check that you have the correct answer is to plug the 7.5 into each one and show that you do in fact get the same answer for either equation. That being said, I'm confident in my physics ability, and so I'm just going to plug it into one, and I'm going to choose the simpler one. See, this only has one term, that one has two terms. Okay, so if I plug that in, I get 7 times 7.5 squared and I get that the collision occurs at position 389 meters. Okay, so remember how we said that because the right car has a greater acceleration than the left car, the collision will take place left of center. And 389 is, in fact, to the left of center because anything less than 500 would be left of center. Okay? So that makes sense with our intuition. It's always good to have to have sort of an answer that you expect. Okay? These accelerations are fairly close to each other. It's not like they're, one is 14 and the other one is 100 meters per second squared, where there's an order of magnitude difference between the two. But so they're pretty close. So I'd expect it to be close to the center, but left of the center. So that gives me confidence that I have the correct answer. So that is where the collision occurs. This collision occurs at 389 meters. Another interesting question I could ask is, what is the relative velocity? For example, so what I mean by relative velocity is, let's say I'm walking towards you at 5 meters per second, and you're walking towards me at 10 meters per second. Because both of us are moving, we're actually going to see, from my perspective, you would be approaching me at 15 meters per second. Okay? So if we subtract the two velocities, that gives us the relative velocity. How fast is it going compared to you from your perspective? If you're on the freeway and you're going at 60 miles per hour and the person in the other lane is going at 60 miles per hour in the opposite direction, that's a relative velocity of 120 miles per hour. Okay? So you subtract the two, 60 minus 60. So to figure out the relative velocity, I better figure out what is the velocity of the first car at 7.5 seconds. So I'm going to use this second kinematics equation. V initial is 0. The acceleration is 14 meters per second squared. The time is 7.5 seconds. So I have 0 plus 14 times 7.5. That gives me a velocity at the time of collision of 105 meters per second. Okay. The second car at 7.5 seconds. Again, it starts at rest. I apologize, class. My internet is not so great today. So at 7.5 seconds, we have 0 minus 22 times 7.5. Where did minus 22 come from? That's because the right car had an acceleration of negative 22 meters per second squared. And so that gives me a velocity of negative 165 meters per second. Negative indicating that it's traveling to the left. So now what I do is I subtract these two numbers to get the relative velocity. 105 minus 165. And that gives me a relative velocity of 270 meters per second upon the collision. That's not terribly realistic. That's almost the speed of sound. Okay? So this is called a collision problem. And they're useful. The second type of more challenging kinematics problem that we will discuss today is called a multi-stage problem. Or, I'll just call it a multi-stage problem. So let me give you an example of a multi-stage problem. A rocket lifts off from rest, okay, accelerating upwards at, let's say, 16 meters per second squared. Okay? 60 seconds into the flight, the engine fails. Gravity pulls the rocket back to Earth. So we want to examine this situation. Now, if this is your first time taking physics, gravity causes an acceleration of negative 10 meters per second squared. Okay? So the defining feature of a multi-stage problem is that we have two or more accelerations. Okay? We have a constant acceleration of 16 meters per second for the first 60 seconds. We have a constant acceleration of negative 10 meters per second squared thereafter. So we have two stages. So this would be a two-stage problem, not a multi-stage problem, but a two-stage problem. So what we want to do is let's analyze the first stage. Okay, so x of t, what is the initial position of the rocket? The initial position is 0, okay? And the initial velocity is 0. So all we're going to have for the x of t is the last term, okay? So we have 1/2 a, which is 16. So 1/2 of a is going to be 8t squared, okay? And then the velocity as a function of time, well, the initial velocity is 0, and the acceleration is 16, so I have 16t. All right? Now, when does the first stage end? The first stage ends 60 seconds into the flight, okay? So let's figure out what is x of 60 seconds, and what is the velocity of 60 seconds, okay? So I'm going to plug in 60 seconds for time. And that's 28,800 meters, 28 kilometers, almost 29 kilometers, and 960 meters per second. All right. Believe it or not, these are actually pretty realistic numbers for a rocket that's going into outer space. Okay. The acceleration of a rocket is going to be in the range of 10 to 30 meters per second squared, because rockets can have humans in them, so they don't really accelerate much more than what a human can handle, or they don't accelerate much more than what the payload can handle, what the structural integrity of the craft can handle. So you're kind of limited in how much acceleration you can have. Okay. That being said, that acceleration lasts for a long time. So even though the acceleration is not that large, you build up a lot of speed. Okay. That's about Mach 3. So that's pretty realistic. Just a minute into the flight, you're already several times the speed of sound, and you're, tens of kilometers into the air. Pretty cool. Now, for a multi-stage problem, the key idea is that the final variables at the end of the first stage become the initial variables for the second stage. Okay, so what if I want, so over here I'll have the second stage. Okay, so I have the second stage, and I'm going to write my x of t for the second stage. Now, what is my initial position for the second stage? My initial position is 28,800. What is my initial velocity for the second stage? Because I need the initial velocity here. It is going to be 960. Okay? And what is my acceleration for the second stage? Minus 10, and it's 1/2 at squared, so I have minus 5t squared. So that's my position as the velocity as a function of time is v initial is 960, the acceleration is -10. So I have 960 minus 10t. Okay? Now, one thing that's kind of interesting to do is to write a position time graph for this motion. Okay? So position in meters, time in seconds. So if we look at this, what does it look like? Well, initially the rocket is accelerating upward. So we have 8t squared, that's a parabola. So we're going to see a parabolic upward arc, something like that, until we get to 60 seconds. Now at 60 seconds, the corresponding elevation was 20. I'm going to make the vertical axis in kilometers, okay? So this is 28.8 kilometers, okay? Now what happens afterwards? Now our position as a function of time becomes a parabola, but this one is concave down, and it has a different curvature. So we're going to see something that looks like this, maybe. Okay? But the slope is continuous because this slope just before the failure was 960, and this slope just after the failure is still 960. So keep in mind that once the rocket fails, it still has a lot of upward velocity. It's not like the rocket fails. It's not like the rocket fails and, okay? It fails and it has velocity, so it continues to coast up after the failure, and only then does gravity pull it back down. So one thing that might be interesting is we could figure out, well, how high does the rocket go? How high does it continue to coast? Well, at the highest point, we know that the vertical velocity is 0. So I can take this equation and I can set the velocity equal to 0. Okay. And we can see that the time is 96 seconds when we reach the highest point. One thing you got to be careful about is that for the second stage, we restarted the clock at 0 when the second stage started. So this is actually 96 seconds after the second stage started, which, if we're counting from the very beginning, is going to be 156 seconds. So I added that to the 60. And then we figure out what was the position at 96 seconds. So x of 96, plugging it into that equation. Okay, so 28,800 plus, there should have been a t here. Okay, I didn't put the t in there. Put it into the live chat if you caught that. If you caught it, put it in the live chat. 960 times 96 minus 5 times 96 squared. So I'm going to plug that into my calculator here. Guess no one caught it. So that gives that the height is 74.9 kilometers. So this rocket coasts basically 3 times as high. Okay. Another interesting thing to do might be to figure out when does it hit the ground. So if I want to know when does it hit the ground, well, the position is 0. Okay. So I could say 0 equals 28,800 plus 960t minus 5t squared. That's a quadratic equation. So I could go ahead and switch over to Desmos. I'm going to type that in. So I have 28,800 plus 960x. I'm putting it as x because it's that's what Desmos understands, minus 5x squared. And we can see this is a parabola. It's a parabola that is so steep that we can't even see the top of it. So we can see it goes up over here and it comes down over here at 218 seconds. So 218 seconds, that is after the first stage begins, or after the second stage begins. 218 seconds later, it hits the ground. So if we are keeping track of total amount of time, this would be 278 seconds. We come back to the ground. Another interesting thing to ask might be, how fast is it going when it hits the ground? What is the slope of this line when it hits the ground? That would be the velocity at 218 seconds. So going to this equation, we have 960 minus 10 times 218. That's negative 1,220 meters per second. Okay? That's really fast. That does not take into account air resistance, so that's probably not terribly realistic. Okay? Now, one of the things that I think is interesting about this problem, and this is going to be a little bit depressing perhaps. There's a really good question. Well, what would happen if it had a second stage? Then basically, if the rocket had a second stage, then maybe you have a position time graph that looks like this. And then if the second stage actually works, then you get a continuation, but maybe a different curvature of the parabola. Okay? So you can see that this parabola is more curved than that parabola. So that would be if you had a working second stage. All right. So I wanted to, so this problem is sort of modeled after the Challenger disaster. So if you don't know what the Challenger disaster was, Space Shuttle Challenger was lifting off, and I don't know when exactly, it was a couple minutes into the flight, so it was not in orbit yet. A couple minutes into the flight, it exploded. Okay. Now, here's the thing. When the Challenger exploded, you know how the Space Shuttle is basically on the back of this giant rocket. Okay. So you have this giant rocket, and then there's 2 solid rocket boosters on the side. It kind of looks like this. Right? And then here's the Space Shuttle right here. That's what it looks like. So here's the main fuel tank, here's the solid rocket boosters, here's the Space Shuttle. So basically in the Challenger disaster, the solid rocket boosters broke off and started going in different directions, and the main fuel tank, which is this thing, exploded. Okay. Now the space shuttle itself remained more or less intact. And according to Newton's first law, it just kept coasting upwards. And then eventually it reached its apex, and then it fell back down and landed in the ocean. Okay. Now here's the part that really gives me goosebumps, and I actually have goosebumps right now as I think about it. They recovered the wreckage of the Challenger explosion, okay? And as I said, the space shuttle crew capsule itself survived and just went into a ballistic trajectory after the explosion. And what they found when they recovered the wreckage was that there were switches on the space shuttle that had been switched, okay? That had been changed. And the switches on the space shuttle are designed so that you can't accidentally flip the switches, okay? You have to, like, it's the kind of switches where, maybe you have to, like, press a button and then that unlocks the switch so that you can flip it. So there's, like, multiple steps to flipping the switch. So the fact that these switches were changed means that someone was conscious while the space shuttle was undergoing this ballistic arc. So can you imagine what that would be like to have known that your rocket has exploded, okay? And you're tumbling through the air you're so high up in the air, you're tumbling for minutes, trying to figure out, trying to orient yourself, trying to do whatever you can to save yourself. It would be absolutely terrifying, and it gives me goosebumps to even think about, okay? So just think about that for a second. Another thing I wanted to mention is that the Challenger explosion completely changed how NASA does launches, okay? Because the conditions for the Challenger launch were not optimal. It was a little bit cold that morning. Okay, and cold temperatures makes some materials more brittle. Okay, and it was brittle materials that brittle materials will fail suddenly. Okay, brittle materials crack; they don't bend; they crack. So it's like you don't know anything's going to happen, and then all of a sudden, it falls apart. It cracks. Whereas, ideally, a material would warp or bend, so you can at least tell that there's a failure coming. So cold conditions made it so that when it failed catastrophically and suddenly. And people knew that they weren't the optimal conditions. People knew there was an issue with. People knew that there was an issue with the brittleness of the materials, but they still launched anyways. So that's called, in NASA lingo, that's called go fever. It's where you get so obsessed with just launching the rocket and starting the mission that you skip over some steps, some safety steps, okay? And so after that, they've put, procedures in place that are designed to prevent go fever and only launch when you're truly ready so that no lives are at risk. That being said, it's an inherently risky business, and it's also an inherently necessary business. I think we've got to keep going to space, even if the rockets keep blowing up. We got to keep trying, because that's what humanity does. All right, I'm going to go ahead and end my lesson there, and I will see you in the Zoom room in a minute or two.